Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will start the new session where we will discuss the balloon tension. In last session we have discussed that the traveler mass is responsible for balloon tension. So, that we will discuss actually. So, balloon tension is basically a function of the rotational speed of balloon and the that is the mass of the yarn. So, okay. So, this is the diagram which we have discussed earlier also. So, the yarn tension in the balloon, that is F b, we can call it as balloon tension. So, yarn tension at the balloon F b is the tension that finally penetrates amongst the spinning triangle. So, from the yarn tension it is getting transmitted through the traveler, okay, and ultimately it is transmitted to the spinning triangle, which actually whatever the yarn breakage in breakage takes place due to the spinning triangle, which is the balloon tension is responsible for that, which is responsible for most of the thread breakage. Okay. Now, we can see here this is the balloon and the balloon tension gets transmitted to the nip point of the delivery roller, where the spinning triangle is there, which is the weakest part of the this unsupported zone. It is reduced to a very small degree by diversion at the thread guide. So, this is the thread guide. Thread guide to some extent reduces, but the contact angle is very less. So, that is why the reduction in balloon tension is not too much, and majority of the balloon tension is getting transmitted to the spinning triangle. Now, if you see the equilibrium force that must be obtained between the yarn tension, that is F f is the yarn tension and the balloon tension. So, the equilibrium force must be obtained. So, since the yarn is diverted at traveler, so this is the yarn is getting diverted at the traveler and friction arises there, the equilibrium is given. So, this is a traveler and this is, suppose this is a traveler and the yarn is getting, just let me draw once again. Suppose this is a traveler okay, and the yarn okay, this is the yarn. So, at this zone there will be friction. Okay. So, this is yarn is diverted at the traveler, okay, and the friction arises there. So, the friction arises at this point and the equilibrium is obtained by F f, that is this is the yarn tension F f and this is F b. So, F f equal to F b e power mu epsilon. So, mu is the coefficient of friction and this epsilon is the contact angle. So, mu is the coefficient of friction between yarn and the traveller surface and epsilon is the angle of wrap, okay, angle of wrap of yarn on the traveller. So, this is there whatever angle. So, the angle of wrap is there. So, value of e power mu epsilon generally lies between 1.2 to 1.8. That means, if this value is 1.2 to 1.8, average we can say it is approximately around 1.5. So, if f will be 1.5 times of f b. So, this is approximately, that means yarn tension is higher by 1.5 times, that is 50% higher. The balloon tension F b is therefore a little more than half of the winding tension. So, that is this is one F b is there. Okay. Yarn tension F b at the point of maximum diameter. So, this is the maximum diameter of the balloon. At the maximum diameter in the balloon can be derived approximately from the following formula given by Professor Krauss. So, this is the formula which is proposed by Professor Krauss. So, that is the yarn tension F b we can calculate, where W L is the angular velocity of the traveller. So, here is the angular velocity of the traveller, h is the height of the balloon, balloon height, total height is h, okay, and this sigma is the specific mass of yarn. This is the specific mass of yarn, that is per unit length, which is takes of the yarn. So, higher the yarn takes, higher will be the yarn tension, and k is a constant. So, from here we can see as the balloon height increases, the yarn tension increases, and the coarser yarn will have higher balloon tension, and if the angular velocity of traveller increases, so balloon tension will increase. So, at higher speed of traveller, so balloon tension will increase. So, thus for a given yarn count, so if we know the yarn count, we can, for a fixed yarn count, the yarn tension in the balloon is strongly dependent on the traveller speed and the height of balloon, because they are related with the power. So, in a square relation. So, if the height, balloon height changes, so the yarn tension increases in a square. So, that will be a great effect. So, higher traveller speed and greater balloon height leads to very high yarn tension, okay, in the balloon. So, a finite balloon can be formed, okay, when there is some mechanism to maintain a yarn tension. So, if the yarn tension is not there, so balloon will be collapse. So, there must be some yarn tension, okay. That means, if we produce a very light yarn, with a very fine yarn, so that means there may be chance of balloon collapse, or else if we produce at a slower speed, traveller's RPM is slower. So, then finite balloon may not be formed. Okay. So, the figure shows, this is the figure that shows the relation between centripetal force, okay, tension T and the work done. So, you can see here this is the tension and here you can see the centripetal force will be there. So, we can see that T V rate of work done. So, V is the velocity, that is the yarn winding speed, and T is the yarn tension, that work done will be the speed of the force into displacement T V per unit time, and 2 T, that is T, and this side also 2 T, that means twice of T will be the this force. M is the mass of yarn present and R is the radius of balloon and omega is the traveler speed. So, centrifugal force merely balance the tension. So, whatever centrifugal force we are getting here, that balances the yarn tension. So, T in both the sides. So, 2 T will be there. So, that is the and where we are getting this m r omega square is the centrifugal force. So, m is the mass, we can assume that mass at the center point. In the ring spinning, the main source of the yarn tension is the friction between ring and traveler. So, that is this tension comes from the friction between ring and traveler. So, circularly polarized vibration. So, circularly polarized vibration is the, it is obtained when a string is made. So, when a string is made to vibrate simultaneously in two mutually perpendicular plane at the same frequency with a phase difference of 90 degree. So, this is important. This is called circularly polarized vibration. Vibration normally in we consider in a single plane, but here the vibration is one is in this direction, another is in this direction due to the movement of yarn. So, this type of circularly polarized vibration takes place in case of the balloon. Now, we can see here the figure at the right side shows the plane and this is the plane vibration and another is the circularly polarized stationary wave on the string. So, this is a plane wave and here is the when we rotate the, because the yarn there is a vibration and that at the same time this is there is a rotation. So, this and rotation and this is circularly polarized vibration, that is okay. Now, so where lambda is wavelength, T0 is the tension of the string and the mass per unit length of the string is m. So, they are related as, so where L length, this is the length is lambda by 2, half of wavelength. So, we can see that L is related with the 1 by 2 f, f is the frequency of vibration and T0 by m, that is related, and m is the mass per unit length. So, from this relation we can calculate, that is 1 by 2 f equal to pi by velocity, that is rotational velocity, and multiplied by under root T by m, and which is equal to pi into P, this is P, where P square is given by this. So, and P will be, P is T under root T 0 by m 1 by omega. So, that is P. So, pi P is there, and velocity propagation is that velocity of propagation C 0 is equal to under root T by m. This is the velocity of propagation. The velocity of propagation of traverse wave is equal to under root T 0 by m only when the inclination of the string to the direction of propagation is very small. So, that is important. Spinning balloons have considerable amplitude, hence there is no unique velocity of propagation. We can see the wavelength of vibration decreases with the amplitude of vibration as shown in figure. So, here amplitude of vibration or per wavelength, and it is actually reducing gradually, wavelength is reducing. So, there is of course an infinite number of possibilities of balloon profile. So, balloon profile can be of any type, okay, different types of profile, and some of the family of sine wave curves indicated by the relation in figure A, okay, that is in figure A and as shown in figure B. These are the different types of wave. Possibly these are the balloon profile, and we can see the wavelength is changing. Now, here at this is the amplitude is lower amplitude. So, amplitude changes for say same wavelength, amplitude also changes, or even the wavelength also changes. So, that is why this type of relationship we can get for all these different types of families of sine waves. So, sine waves have got their different types. The spinning balloon of any kind is in equilibrium, essentially a stationary wave system formed by circularly polarized transmission. So, transverse vibration is there. So, this is the circularly polarized vibration. A small traverse wave in the string. So, for small traverse wave, so this relationship we know. So, lambda will be 1 by f T 0 by m. So, and C 0 is equal to under root T 0 by m. So, it will be C 0 by f, lambda is equal to C 0 by f, where C 0 is the velocity of propagation. So, here there is not simple vibration, the vibration propagates, okay. Lambda is wavelength, T 0 is tension of the string, that is yarn tension, we can say in the present case. M is the mass per unit length of the yarn. The stationary wave pattern are formed in a string with both ends fixed. So, if we fix both the end, when the length is an integral number of half of wavelength. So, that for that case we can get the stationary wave pattern. Now, we will see how the shape of balloon changes in absence of air and in presence of air drag. So, that is why in absence of air drag what happens, let us see. So, this is the balloon shape, normal balloon shape in absence of any air drag. So, there will be a smooth balloon shape will be there if in case of no air. The force acting on the yarn in the balloon lies in the axial plane when there is no air drag. Okay. Velocity of the yarn along its length is negligible when compared to the rotational velocity. That means, in that case balloon that is forces on the yarn lies on the axial plane. So, we are neglecting the velocity of yarn as compared to the rotational speed, no air drag, the friction between yarn and lappet is negligible. So, there is no disturbance there. So, it will there is no disturbance by the lappet, yarn stiffness is negligible, yarn is highly flexible we are assuming. So, mass per unit length of the yarn is m, omega is the angular velocity, T is the tension. So, these are the assumptions here. Now, let us see, consider the force acting on an element of yarn with the mass per unit length m in the balloon is shown. You can see now here from this diagram where force acting on an element of the yarn in the balloon where delta t cos theta. So, delta t cos theta, this is t, okay, t cos theta, this is theta, t cos theta will be in this direction. So, delta t cos theta means small increase in delta t cos theta, it is equal to 0, and delta t sin theta, that is the delta t sin theta will be m, delta t sin theta will be m r omega square delta s. So, this will be in the, it will be mass negative in the sense. So, this is working in this direction, then delta t sin theta will be here delta t sin theta. So, because this is here it will be delta t cos theta. So, that will be minus m r omega square delta s now sin theta equal to delta r by delta s. So, we can see that sin theta will be delta r by delta s, that is sin theta So, here it will be delta, this is the delta S, so from equation 1 what we get, you can see that from equation 1 delta t by t equal to tan theta delta theta. Okay. So, this we can get here from equation 1 and 2, if we use this. So, we will get and from equation 2 we will get this one T cos theta delta theta and sin theta delta theta. So, that we are getting. So, here we can see this we can simply get by, so T cos theta. So, we will just I will try to show you the how we are getting from the equation 1 this one. So, if we differentiate T cos theta, so we will get T delta d cos theta means minus sin theta d cos theta sin theta and plus minus sin theta plus cos theta okay. That will be this and this there will be T cos theta okay. T is delta T cos theta delta T okay. Now equal to 0, that means cos theta delta T equal to T sin theta. What we can get delta T by T will be sin theta and cos theta sin theta by cos theta. So, that we can directly calculate from this okay. Now, T d theta. So, T d theta sin theta and then we are getting delta T by and T cos theta d theta. So, that means sin theta by cos theta tan theta d theta. So, we are getting this relationship. So, we can derive this relationship from this and by differentiating this equation we will get this equation. Okay. So, that is possible. We will get now from equation 4 and 5. What is equation 4? This is equation 4. T delta T equal to delta T delta theta equal to delta T by tan theta, that is equation 4 that we have already got, and equation 5 sin theta equal to delta r by delta s, equation 3, and substituting equation 5 what we are getting, this is equation 5. So, from just a minute, from this equation 5 what we are getting, this will be T cos theta d theta plus T sin theta d theta. We can get if we replace this one in equation number 5 okay. From equation 4, what is equation 4? T delta theta by equal to delta T by tan theta. And now, if we replace this, we will get equation number 6. What is that? M r omega square delta is equal to minus delta T sin theta, that we are getting, and from there we are getting that from equation 3 and 6, equation 3 and equation 6. So, we will get, you just replace the sin theta here. So, what we are getting, m r omega square dr equal to minus delta t, and integrating equation number 7, if we integrate, so we will get half m r square omega square, that we will be getting equal to minus t and plus constant when r equal to 0 and t equal to 0. So, if we use r equal to 0 and at Young tension T, the constant will be T T0, the constant is T0. So, that we can use here. So, initial tension T0. So, ultimately we will get equation number 8, T equal to T0 minus half m r square omega square. So, that is the tension. So, from equation 1 what we are getting, this is the equation 1, we get that value T cos theta equal to T0 cos theta 0. Okay. And from equation 8 and 9, so this is this two equation we are getting cos theta and T, we are replacing this value cos theta, and we are replacing T value with the T0 half m r square omega square equal to T0 cos theta 0. So, this is the relationship number 10, but we know P square equal to T0 m omega square. So, with no air. Now, here what we do, the P square we are, the T0 we just replace here. So, equation number 10 becomes, this is equation number 10 becomes cos theta P square minus r square by 2, just replacing this from equation number 10 we are, and equal to P square cos theta 0. So, that we can replace here. So, cos theta will be cos theta 0, okay, and rearranging this equation will be 1 minus 0.5 r by P square. So, that is the relationship cos theta we can calculate, and now this equation provides the inclination of the yarn at any radius, So, that yarn inclination changes at any radius, inclination of the yarn, and thus enables the exact shape of the balloon curve for a given theta 0. So, for any initial angle theta 0, we can calculate the angle shape of the balloon for different value of r and p. Now, with air drag, so without air drag is ideal one. So, from there we know the actual shape of this. Now, here if we add this air drag, so there will be only deviation due to the air drag, but basic concept here we can calculate, we can actually this predict the shape of the balloon. Now, with the air drag what happens, you can see the air drag will try to push the balloon backward. Okay. So, the effect of the balloon is moving in this direction, so air drag will try to push back. So, for a smooth cylindrical cylinder, so placed in normal to the air stream. So, one smooth cylinder which is placed normal to the air stream, what happen, air drag force will be half C1 P V D V square D. So, where C1 is the drag force, okay, and P is the density of air, V is the air velocity. So, speed of air, and D is the diameter of the cylinder. So, any cylinder when it moves, so it will have a drag force. So, this is the standard formula and the primary effect of air drag is that work must be done to rotate each element of the yarn. So, it is rotating. So, that will be the drag, air drag. So, each element has to move against the air drag. So, that we have to work, each element must be acted upon by the force with a moment about the axis. So, with the tangential component. So, this about the axis, the work done we have to calculate. At the lappet, the tangential component of the tension is 0, because that is the starting point. We can see here the lappet, and at the traveller it must be such that its product with the circumference of the ring is equal to the total work done per revolution of the rotating loop of yarn between the traveller and the guide. So, that means total its product with the circumference of the ring. As a result, the difference in the tangential component, the yarn will be inclined to the axial plane. So, in normal case it should be equal. Okay. This actually the work done per revolution of the rotating loop should be equal, okay, at any point, but as a result of difference in the tangential component, the yarn will be inclined. So, it is not will be at the axial plane. So, air drag acts as an angle to the axis of the yarn. Okay. There will be a vertical component of air drag acting downward, and air drag has a stabilizing effect on the balloon shape against the mass variation. Now, effect of air drag, and that is why we have multiple balloons if the air drag acts. So, in absence of air drag, the true node forms, since there is no tangential component when the height of the balloon is great enough. Okay. But when the height of balloon is greater, in presence of air drag, the radius of rotation of each element must remain finite, as the work done is tangential component times the circumference of the rotation. So, that is why a true node cannot be formed, and instead neck of finite radius is formed. So, there will be neck formation. Now, we can see effect of traveller. So, what we have seen the effect of air drag, now effect on the traveller. So, all the forces mentioned here act here on the traveller, since the force themselves and their angle of attack are constantly changing. The attitude of the traveller in the ring frame also changing. So, this traveller will also change. This analyzable variation are reinforced by sudden sharp force arising from the balloon or from the friction condition between the ring and traveller. Quite uniform and stable running of the traveller is therefore impossible. So, there will be multiple forces acting on the traveller. So, traveller will always try to adjust on its own. So, there is smooth and uniform stable running of traveller is not possible. This is one of the greatest problem in the ring spinning. So, that is why the traveller, the still bigger problem of traveller is the heat generation. So, traveller has got the instability problem, and also there is a problem of heat generation. So, the heat is generated due to the friction between ring and traveller, and the main problem here is that the heat dissipation is not possible, it is not done, it is not easily done because of the conduction is because of the very low mass and that low contact area, okay, with the ring. If the ring and traveller contact area is high, then their heat dissipation will be easy, but air being a insulating insulating a heat insulator. So, heat is not easily getting transmitted through the air. The problem here is actually not so much generation of heat as its dissipation. So, generation of heat will be there, but heat dissipation is a problem through the from the traveller. So, you can see this is a ring, okay, and here is the traveller. Now, from traveller heats actually the quantity Q tier conductive heat from ring to traveller. So, from ring to traveller the conductive heat goes, and from traveller to ring the conductive heat is transmitted from the. So, there is a heat exchange. Now, the conductive heat from traveller to ring should be high, because the ring has got higher area, okay, that is higher volume. So, it can absorb heat, more heat, but traveller being a very small in surface area, and that there should be very quick heat conduction from the traveller to ring, but that is only possible when the contact area between the surface of ring and traveller is high. And in the modern traveller, ring traveller zones, that is the process along with the other development, the contact area between ring and traveller is actually increased, that we will discuss subsequently when we will see the high speed traveller ring. Now, the heat is getting transmitted from the traveller by convection, conduction and radiation. So, convective heat transmission will be there because the traveller moves at faster speed. So, convective heat transmission is there, but conductive heat transmission is very less, and also radiative heat transmission, but radiative heat transmission will be low because the temperature difference is not that much. So, it also because when the traveller temperature increases, in that case the radiative heat transmission will be high. Since the traveller has no drive of its own, but it has to follow the spindle, it moves, its movement must be braked. So, that, and it is done by the frictional contact. However, braking without generation of heat is not possible. So, that is the problem. One is we have to have brake of the traveller movement, and for that we need higher frictional force, and higher frictional force resistance means higher heat generation. So, accordingly a very high temperature arises in the traveller, they reach more than 400 degrees Celsius. So, the 400 degrees, sometime the traveller burnout takes place at this high temperature. So, the mass of the traveller is too small to enable to transmit the heat to the air. So, for if the surface area is high more, that means that will actually release the heat quickly, both conductive, convective and radiative, but if traveler is size mass is very small, okay, and to the ring surface. So, as I have mentioned, so its mass is very small and so its dimension is very small. So, its transmission to the heat to the ring is also very small, very little. This various explanation shows that it is not easy to achieve considerable improvement in the interplay between the ring and traveler and yarn under present condition. So, that is why the development of ring and modern ring and traveler is there. In the next session, we will discuss the shape of ring and traveler to improve the speed, the increase that enhance the for the high speed spinning, what type of ring and travelers are being developed. So, even with the completely new design of ring and traveler as introduced by different manufacturer, traveler speed limits is approximately 50 meter per second. So, that is the limitation. So, that is why in ring spinning the limitation of speed is the limitation of traveler speed. So, traveler sliding speed we cannot go too much, okay. That is why we cannot have very high productivity in the ring spinning. Otherwise, on all other aspects ring spinning is can actually produce a very good quality yarn. Only the productivity is limited by the traveler speed. We will stop here. In the next session, we will discuss the high speed ring and traveler. Till then, thank you.